Hello, in this video we're going to discuss subsequences of real numbers. But first let's define it. So let's let AN be a sequence of real numbers. So that means a 1, 2, 3, 4, and etc. Now a subsequence of AN is just picking terms from the original term. Okay, and picking terms, you can think of it in two ways. So here's an example of a subsequence where we pick the second, the third, the fifth, the AK-1, and we keep going like that. Then this is a subsequence of our sequence AN. Now, some people also think about removing terms, and then what's left is the subsequence. So if we remove A1, remove A4, remove, and then what's left is our subsequence. But I really like to think about it as picking the terms from our original sequence. Okay, so now here's our subsequence, and generically we're going to let it represent AN1, AN2, AN3, AN4, where these numbers here are strictly increasing. Okay, and the reason that we subscript it like this is because this subscript on the subscript tells us what term we are in our subsequence. Okay, so in this example, N1 was 2, right? N2 is 3. N3 is 5, right? And so this is how we're generically going to build subsequences. Okay, and so again, generically, a subsequence of AN will be noted by AN sub K. Now there's a few notes here that when you're picking a subsequence, you can't change the relative order, meaning we couldn't have put A2 first and then A1 second, because that's switching up the terms. You can only kind of go in order. Okay, so we'll go through some notes here. Cannot change the relative order of terms. Now the subscript on NK, which is K, it denotes that it's the kth term in our subsequence. The limits of subsequences are actually defined in the usual way. So if L is a limit of a subsequence, that means there's an epsilon greater than 0, and there exists an N such that when N sub K is greater than N, then this limit holds. That means that we're getting really close to this limit L, for any small epsilon. Now, that means L is called a subsequential limit of our original series AN. It's actually it's a limit of our subsequence, but it's also a subsequential limit of our original series. Now here, I must admit, some people do this differently. There exists a K, capital K, such that little k greater than big K, this holds. So you can really focus on that little sub index, and it ends up being the same thing. Here's another note, that NK is always greater than or equal to K. This is for all K. And so I'll go back to our example here. So this is K. K is 1, but NK is 2, right? So K is 2, N2 is 3. So this number is always actually always greater than or equal to this number. Now they can be the same. So if we have our original sequence and then we pick the same, each element from our sequence to be our subsequence is actually the same sequence as our original sequence. So that's a possibility. So now let's do a theorem here. A sequence AN converges to L if and only if every subsequence of AN converges to L. So since it's if and only if, we assume this is true and prove that, and then we have to assume this is true and prove that. So let's go this way. So we assume that the sequence has a limit, call it L, then given epsilon greater than 0, there exists an n such that n greater than n, we have this as true. Now, let's let k be greater than n. Then our n sub k, which is greater than k, actually that should be equal to, but k is greater than n. Now notice that so n sub a sub nk is actually past a sub n in the sequence. And this, since our sequence converges, every term past this capital N meets this requirement. So we're creating the condition that our subsequence, remember, and it's picked from terms from original sequence, is past the a sub n that meets this requirement. Thus, our subsequence meets this requirement. Therefore, our subsequence, any subsequence we pick, converges to L. Now let's go back the other way. So define the subsequence a sub nk where nk is k. So that means that our subsequence is the original sequence. And since every subsequence converges to L, that means we have our original sequence, in this case, converges to L. So it is true. Now, one note here is that every subsequence has to converge to L for this to be true. So let's say our original sequence was 1, 2, 3, 1, 2, 3, 1, 2, 3, and etc. So the original sequence doesn't converge. So this theorem doesn't apply, but notice that the subsequence, if we pick every third term, it either converges to 1, 2, or 3, depending upon which term we pick first. And so we have subsequences that converge, but not all of them converge to the same number. So the original sequence doesn't converge to that same number. So here we're going to look at a theorem that I'll prove in a later video, maybe. So the number L is a subsequential limit point of an. If and only if, for epsilon greater than 0, this interval contains infinitely many terms of an. Okay, and so what that means is that if we have our original sequence 1, 2, 3, 1, 2, 3, and etc., then let's let L be the number 1. Then this interval 1 minus epsilon and 1 plus epsilon, it contains infinitely many terms of our original sequence, right? 1, 2, 3, 1, 2, 3. So L is a subsequential limit point of an, but also 2 is a subsequential limit point and 3 is a subsequential limit point of our original sequence. Okay, and I'm pointing this theorem out because a sequence can have lots of different subsequential limit points. Now, when we start talking about the supremum of all the subsequential limit points and the infimum of all the subsequential limit points, that gets into what's called a limit supremum and a limit infimum of our original sequence, which in I think 3 or 4 videos from now, we're going to discuss limit supremum and limit infimum. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.